Hey guys, welcome to lecture 17. So this is the second lecture from chapter number 4. So in this lecture, we will use derivatives to sketch the graph of a function. In fact, we will continue with more qualitative properties of the derivatives. In fact, in this lecture, we will discuss we'll talk about the first derivative test, second derivative test. You'll see last time we have seen what the critical number is or critical point is. Now you will see what an inflection point is and so on. All right, so let's get started. So I would like to start with some properties of functions, of monotone functions, in fact, right? Okay. So let's get started. So I'd like to start with with monotone strictly increasing functions. So at this point, we will like to relate the derivative with in fact, we would like to see what is the connection between increasing, decreasing, in fact, what is the connection between monotone functions and derivatives. All right, now let's go back to the definition of a strictly increasing function. Sometimes I will avoid the word strictly increasing. I will just use increasing. So once I use this, you will understand that it's strictly increasing. And when I say it's non-decreasing, I mean it's increasing, but not strictly. Okay, so the definition is that the function f is, and I will put it like this, strictly increasing, so it's increasing. On the interval I, if f of x1 is strictly less than f of x2 whenever x1 is less than x2, right? And with x1 and x2, are in this interval I. So there are points in the interval. So this is the definition of a strictly increasing or increasing function. And as you can see now, let me put it like this. We can, in a similar fashion, we can define decreasing functions. So the definition will be very similar. Okay, so we will say that the function f is strictly decreasing, right? Or I'll just say simply decreasing on the interval I. If this time we will have that f of x1 will be strictly greater than f of x2 whenever x1 is less than x2, right? And x1 and x2 are in I. Okay. And now we would like to say so about monotone functions. A function is f, let's say, is said to be monotone. Right? on an interval I, if it is either increasing or decreasing, Of course, I mean strictly increasing, strictly decreasing on the entire interval I, right? So that's what you need to know. And now, like I said, there will be a theorem which will relate the derivative of a function to the monotonicity. And this theorem is called the monotone function theorem. So theorem 1. So we'll call this monotone function theorem. Okay, all right. And this theorem says the following. Says that let f be a differentiable function right, on the open interval AB. And now the theorem states the following. If f prime of x is greater than 0 on the interval AB, on the open interval AB, then f is increasing. On AB. Okay. Now, if the first derivative of x, so f prime of x is less than 0 on AB, then f is decreasing. On AB. Right, so this is the monotone function theorem. And now let me just picture this a bit. I want you to see geometrically what do we mean by that. Right, I want you to, well, look at it again. And now we would like to see how graphically how this would look like. And let me show you a picture. So here I'll show you a picture with the increasing function. And in this case here, I'll show you something with decreasing function. We would like to see, okay. So let's just say we have something like this. And now we just draw, you see, something like this. Then I have some, ooch. Let me draw some tangents for my, you'll have something like this here, and so on. Okay, so as you can see, the graph is rising, so the function will be increasing. And now let's picture something decreasing. So let me just draw it again. Let me just say I have something like this. And here I'll have, let's just say, like this, then like this. Okay, so as you can see, let's point out what we observe on this graph. So here, note that the slope of each point is positive, which means that f prime of x is positive. All right. The same situation will be here. We note that the slope of each point is negative. So positive and negative, which means that the derivative will be negative, that f prime of x is less than 0. Okay, so this is the scenario. Right? And now I would like to say a few things about the first derivative test. This is very, very important. So the first derivative test. Well, basically this will relate. So why is this so important? Because it will allow us to find a relative, so it is useful for finding the relative minimum and relative maximum. Right? All right. And now let's see what this is all about. So we will follow some steps here. So step 1, in fact, let me write it with red. Step 1. Well, we need to find all critical numbers. So find all critical numbers of a continuous function continuous function f defined on an open interval AB, let's say, on an open interval AB. All right. All right. Now step 2. We need to classify each critical point so we need to classify each critical point, let's say x naught f of x naught. Let's just say like this, as follows. Okay, and here we have something. So A. If the derivative f prime of x is greater than 0, then the graph is rising. So the graph of the function f is rising. Right? For all x in the interval a x naught. So keep in mind that x naught will be my critical number. Now b, well, wait. We also have, in fact, let me write it. So we have this situation. So if f prime of x, okay. Now, if f prime of x is less than 0, then the graph is falling. Then the graph, okay, the graph of f is falling. Okay, it's falling for all x in the interval x naught b this time, right? So, and let me just draw a picture so that you can see better. And then we can say that, the point x naught, f of x naught, right? This point is a relative max, and let me write it, relative maximum. Okay. And the picture will be quite clear. Let me just draw it. So let's just say we have the following situation here. Let's just say here I have the point A, here I have the x naught, here I have the point B, and let's just say here I have f of x naught. So this is where my point of coordinates x naught, f of x naught will be here, right, as you can see. And let's just say that the graph, so let me say that we have here another point, and now the other point will be somewhere here. So the graph will go like this, right? So as you can see, on this portion from a to x naught is on this interval, it will the function is decreasing, and then starting from x naught all the way to b on that portion of the interval will be increasing. So that's what we're going, and we can write this in the following way. So I'm just going to draw this arrow is going to fall all the way here to this point, x naught, f of x naught. And starting from here, it will increase, right? Wait, I think I draw the graph is rising. Okay, no, okay, I draw the other situation when it's the other way around. Okay, let me do it again. My bad. Let's just say here we have the point A, here we have the point B, here we have x naught. Let's just say here we have, so I'm going to draw it somewhere around here. So this will be my point. So this will be f of x naught. So here is f of x naught. All right. And let's just say that somewhere around here, right, is my point, and somewhere around here is this. So the graph will be something like this. It's right. As you can see, it's rising on the interval a x naught, and then it's falling from x naught to b. So we can express this. So let me write it. I will put an arrow here all the way up to this point, x naught, f of x naught. and then it will just fall. Okay, B. F prime of x is less than 0. So we have this situation. So if, okay, let me write it like this. If f prime of x is less than 0, then the graph is falling for all x in ax naught. And now if f prime of x in this case will be positive, then the graph is rising, then the graph is rising for all x in x naught b. And then at this point we can say, so then we can say that then the point x naught f of x naught is a relative minimum. Okay, and now we can draw, so let's draw a picture so that we can see it better. Just say here it's f of x naught. So it will be somewhere around here. So this is the point x naught f of x naught, and let's just say it's this here and this one here. So as you can see, the graph goes like this. So it's quite clear that from on the interval a x naught, the graph is falling, and then starting from x naught all the way to b, the graph is rising. So let's just write this with arrows. So this is falling here, and we'll call this the our point of coordinates x naught f of x naught, and then it's rising. All right, so this is the second scenario, and now the third one. See, f prime of x, so the derivative of x, has the same sign for all x on the interval ax naught and x naught b on each side of x naught. So if this happens, then the point of coordinates x naught f of x naught is not an extremum, is, let me write it here, not an extremum point. This is very important to know. Okay, I want to stress this out. This is important. Right? So we don't know that, right? Okay. Now let's see an example. I'd like to illustrate the first derivative test through an example. Well, like I said before I go and do this example, I want you to look at it again. So as you can see, basically we have to, step one again, we need to find the critical numbers. Then once we have those critical numbers, we have to classify them. and then you will see you classify them by computing the first derivative, and you'll see how the graph is rising, how the graph is falling. So you would like to see on what interval basically the function is increasing or the function is decreasing, right? And then based on this, you can decide whether that the critical point is a relative min or a relative max, right? Or neither of them, based on what you have seen so far, right? Okay. And of course, if the third scenario is that if the derivative has the same sign for all x, then for all x in both intervals, a, x naught, and x naught b, then on each side of x naught, then the point is not an extremum point. Anyway, let's see some example, and I have in mind, so let me consider this function. Let me just take the following function. Let me take a cubic one. So x cubed minus 3x squared minus 9x plus 1. Okay. So clearly this function is defined on the entire real line and real valued. Well, it's quite clear. It's a continuous function. Is actually differentiable. You can differentiate here. You don't have any problems in taking the derivatives. All right. So now let's compute. So first we need to find the critical numbers. And now we compute the derivative. So first we find the critical numbers. All right, how are we going to do that? Well, we have that the first derivative is given by, the first derivative is 3x squared minus 6x minus 9. As you can see, this is a quadratic function, and in fact, we can decompose this. So this would be nothing other than 3 times x minus 3 times x plus 1. And the critical numbers are given by, well, you set this equal to 0, right? And these are x equals -1 and x equals 3. So these are my two critical numbers. And now I have to decide, well, what are they? Are they relative min, relative max, or neither of these? All right, so now we have these critical numbers, and now we evaluate our function f of these two critical numbers. So we'll have f of -1 will be 6, and f of 3 will be -26, right? So the critical points are given by what? So let's just say P1 of coordinates -1 and 6, and P2 of coordinates 3 and -26. All right, so these are the two critical points. And now we'll ask the following question. So the first question that we would like to ask is, where is the function f increasing? And when I say where, I mean on what interval? All right. So in other words, what do I mean by the function to be increasing? It means that when is the derivative positive? And now let's see. So f prime of x is positive if and only if, and let's see who the 3 times x minus 3 times x plus 1 is positive. All right, what does this mean? This means that the 2 is positive, so one of the parentheses must be negative, right? So in either case, x will belong to, will take all the real values except all the values between -1 and 3. So x will be right here. So once we draw this, so let me just say here I have -1, and here I have 3. So it will be anywhere here. Right? Okay, so the function is increasing. So this will be equivalent with x is less than -1 and x is greater than 3. So let's keep this in mind. Okay, now the question 2, well, similarly, where is the function f decreasing this time? Well, in other words, on what intervals? And when we say decreasing, I mean f prime of x is less than 0. So this is what we mean, right? So the function is decreasing. This means that the derivative f prime of x is less than 0. This happens if and only if 3 times x minus 3 times x plus 1 is less than 0. And at this point, where this is less than 0, and this happens if and only if x is between in this interval, -1 and 3, open interval, right? So -1 is less than x and strictly less than 3. So when we draw this here, this is -1 and 3, right? These are the values on this interval, except the endpoints on the interval. So -1 and 3 will exclude them. Right? Now at this point, we see when the function is on what interval the function is decreasing, on what intervals the function is decreasing. And now we would like to classify these 2 points. So let's see. So classification of P1 and P2. So how do we classify them? So the first one, P1, of course, what was, so -1 and 6. And then, so it will be like this. So P1 is a relative max. It's a relative maximum. And the same thing happens with P2. Well, it will be, well, as you can see on the first part, the function is decreasing, then it's increasing. It will be P2 is a, so P2 is a relative minimum. Okay. Now let's postpone drawing the graph of this function. We'll draw it afterwards. All right, so this is basically the story with the first derivative test. And we would like to see now what happens when we deal with the second derivative test. But before we go and talk about that, let me just say something about concavity and inflection points. So let me just draw some pictures, something like this. And let me just say here I have a point P. And let me draw a tangent line here, right? So the graph lies below the tangent line. So let's mention that. So the graph lies below the tangent line. And now, if I draw something like this, let me say I have here point P, and let me just draw the tangent line. See, something like this, right? And the tangent line in this case, so the graph lies above the tangent line. Okay, so imagine these two situations. And now we would like to see what it means to be for a function to be concave up. So let's see. So we have seen what it means for a function to be increasing, decreasing. Now let's see concave up and concave down. So concave up means that, let me write it with red, the graph, sometimes concave up we call this convex or whatever. So the graph lies above all of its tangent lines on an interval I, right? And then it's said to be concave up. This is what it on I. So let me just draw this picture. So let's just say we have something like this. And let's just say I have here A1 and here I have B1. And the graph should be something like this. So this is concave up, right? Okay. So the tangents are below the graph, the tangent lines. Okay. And now we would like to see what it means for the concave down. The graph lies below this time. So in the first case it was above, then now it is below all of its tangent lines. Right, on an interval I. And now let me just draw a similar picture. So let's just say we have something like this. And now all of its tangents are above the graph, right? As you can see. All right, so these are the two situations. And now we would like to see what is the connection between the derivative and concave up and concave down. So we would like to, so derivative characterization of concavity. So we would like to address this. And we say that the graph, in fact, let me write it with red, because this is basically, so the graph of a function f is concave up on any open interval I, where, guess what, the second derivative will be positive, where f second prime of x is positive. And concave down and, okay, let me write it. And concave down on any open interval I where the derivative, guess what, is negative, the second derivative. So that's the derivative characterization of concavity. And I would like to show you an example of this. In fact, we would like to continue with the first example. So let's go back to example. Let me consider let f of x to be, what was the function? So x cubed minus 3x squared minus, so x cubed minus 3x squared plus 9x plus 1, I think, right? Minus 9x plus 1, okay, sorry about that. Here it's a minus. And f defined on our reals and with real value. Okay. So now we compute the derivative. So the first derivative was given by, so f prime of x was 3x squared minus 6x minus 9. And the second derivative, if we compute this, f second prime is nothing else. Well, so the second derivative is the derivative of the first derivative. Let me remind you this. So this would be nothing else than just 3x squared minus 6x minus 9 prime. And now using the sum difference rule, this would be nothing else than just 6x minus 6. Or if you want, is 6 times x minus 1. So that's the second derivative of f. And now we, based on the derivative characterization of concavity, we have the following. So f second prime of x is positive, right? Which will be equivalent with 6 times x minus 1 is positive, which will imply that x is greater than 1. So on this, it follows that f is concave up. And now f second prime of x is less than 0, which will be equivalent with this guy, less than 0, which implies that x is less than 1. So f will be, f is concave down. Right? Okay, and that's it. This is where on this interval, when x is greater than 1, the function is concave up, and then for on the interval for which x is less than 1, the function is concave down. Now let's talk about inflection point. So let me stop here. So inflection point. Well, as you can imagine, there must be something for example, on the graph of a function. At some point, if I have a function on which is on a certain portion is concave up, and then it goes concave down, then that point where this situation changes will be called the inflection point. So keep in mind, the critical point has to do with where the function changes from increasing to decreasing or the other way around, right? And the inflection point, it has to do when the function is changing from concavity up to concavity down or the other way around. So keep that in mind. Well, let's write it. A point, let's say P of coordinates x naught f of x naught on a curve is an inflection point if the graph is concave up. On the side of P and concave down right on the other side. Let me put it this way. So in other words, let me just draw a picture so that you can see it better. So suppose I have a function that goes like this. Here I have the inflection point P of coordinates x naught f of x naught, right? This is concave down. This portion here is concave down. And this portion here, starting from P, is concave up. And let's just say we have a similar situation. Let's just say it goes like this. So here will be my point P of coordinates f x naught f of x naught. So here we have concave up. And here will be concave down. So that's what an inflection point is. And now let's just continue with the example. So we have seen here. Now let's go back to our example. Right? We have seen that, look at this here. We have seen that for x greater than 1, my function is concave up. And for x less than 1, the function is concave down, right? Okay, that's beautiful. And now we would like to see, so now we continue. So continuing with the previous example. It follows that for all values x which are greater than 1, f is concave up, and for all values x which are less than 1, f is concave down. Well, in this case, we can say that this means that this point of coordinates 1 and f of 1 is an inflection point. And now let's compute f of 1. So we have that f of 1 is -10, right? So this guy here is nothing else than just P of coordinates 1 and -10. So this guy is an inflection point, right? So at this point now we know what's an inflection point. We know what it means for a function f to be concave up, to be concave down. Well, now we're in the position to say a few things about the second derivative test. Well, it's just like with the first derivative test, this is also important because it will not just allow you to classify critical numbers, but it will allow you to classify the inflection points. So, but before we go into, in fact, you know what, before I even go and talk about second derivative test, yeah, let me just say a few things about second order critical number. So we would like to say a few words about this. All right, the number x naught, right, is called a second order critical number. Now, in fact, let me write it like this. Right? So if the derivative at that point, the second derivative, if f second prime of x naught is 0, right? Or the second derivative at that point does not exist. Does not exist. Okay. So they're simply the critical numbers of f prime of x naught. So let's mention that. So these are simply the critical numbers of f prime of x. Okay. Now let me point out some remarks here. So some remarks. And the first remark I want to point out is following. Let's say the ordinary critical numbers right? Where let's say f prime of x naught is 0, or f prime of x naught does not exist, right? Will be called first order critical numbers. So will be called first order critical numbers. From now on, right? So this is how we're going to call them. And now the second thing, which is very important and that I would like to mention, the concavity of F will change only at the second order critical numbers, only at the second order critical numbers. All right, now let's continue with our example. So going back to the previous example, we have, let's see. So remember we had, let me see. So it was the second derivative 6, okay. So the second derivative, right? So we have that the second derivative of x was 6 times x minus 1. So the second derivative of x is 0 if and only if x equals 1. And now we can say that this guy 1 is a second order critical number. If you want, or an inflection number, whatever you want to call it. We call it second order critical number. Okay. So notice that the concavity will changes at this point. So the concavity, so let me point this out. The concavity changes at this point. This is important for you to know. Okay. And now, finally, we're in the position to talk about the second derivative test, and then we'll continue with the example. We'd like to see which one is a relative min, relative max. Well, we like to use a second derivative test to the second derivative test. Okay, so the second derivative test, let me say it is useful to find, again, relative minima and relative maxima. So you have two options, two procedures to find a relative min and a relative max. So you either use the first derivative test, or you can even use the second derivative test. So to find relative minima and relative maxima. So this is why is this useful, but you will see that it will involve the second derivative. And let me just say, so step 1, find all first order critical numbers. Okay, and step 2, we would like to classify each critical point x naught f of x naught as follows. If the second derivative at x naught is positive, right? Then there is a relative minimum. And second, if f second prime of x naught is less than 0, then there is a relative maximum. And the third scenario is that if the second derivative at the point x naught is 0, then the second derivative test fails. So there might be a relative minimum, a relative maximum, or neither. Or neither at the point x equals x naught. Now let's continue with the same example. So we continue with the same example. And we would like to classify the points, and we have. Let's summarize what do we have. So we have critical numbers. So the critical numbers are x equals -1 and x equals 3. Remember that? And the second derivative, remember it was 6 times x minus 1. And we know that the second derivative is this guy here. And now, if we look at the second derivative test, what we need to do is just to evaluate the second derivative at those critical numbers. And then after we do this, based on the second derivative test, we classify which one is relative min, which one is relative max, or which one is neither of these. Let's do that. So we have that f second prime, now let's see, of -1 is -12, which is less than 0. So this means that this point x naught equals -1 is a relative maximum. Right? And when we compute the second derivative at the x naught equals 3, so we will have that this will be 12, which is positive. So this will give us x naught equals 3 is a relative minimum based on the second derivative test. Note that we got the same result by using the first derivative test. All right, now the big question is, after we did all this, we would like to actually graph this function. We want to see how this function would look like. All right, let's do that. And then, so let's go back. Now, the question is, how do we graph this function? So the function f. That is a big question. And now let's see, keep in mind that f of x was, what was it? So it was x cubed minus 3x squared plus 9x minus 1. Minus 9x, sorry. Plus 1, right? Yeah, that was the function. Okay, now keep in mind that this is f prime of x was a 3x squared minus 6x minus 9, and f second prime of x was 6x minus 6. Okay, so these are the derivatives. And now let's put all this information that we got, let's put all this information on the same. And now let me just draw the graph. I'm going to draw a big one because I want to I hope you'll see it. Anyway, this is x, y. Now let's see, here I have the point 0. Let's see, what other points do we have? So I have 1, negative 1, sorry. I have 1 here. What else was there? I have 3. Let me put it here. And then at some point I have, oh my. So I have negative 10 here. So this was an inflection point. And then let's see, what else did I have? 3 and negative 26. Okay. Here I have negative 1 was 6. You just put it, okay, here. And this is 1, the y-intercept. Okay, and here will be the relative min. All right, so the function will go like this. So let me draw the function first. Boo, it will go through this point, and then it will go through this here, and then it will intercept this point here, and then it will go here, and then it starts rising like this. So this is the graph of my function f. Look at it. As you can see, now let's interpret this. Right? Let's interpret this. Okay, so this guy here, is an inflection point. This guy was, as you can see, this guy is a relative minimum. Well, as you can clearly see from the picture, this guy here is a relative maximum. Right? So this guy here, let's say this is the y-intercept. This guy here, okay, and that's it, right? All right, from here to here, from here. So on this portion here is increasing, as we have seen. Then well, this portion here so here will be decreasing. But all the way from here to here will be concave, concave down, right? All the way, so concave down. So all the way from here to here. Right? As you can see from the picture. Maybe I shouldn't write, but I don't want to ruin the picture, but because you can see clearly. Okay, from here to here, this will be decreasing. I'm just going to write it like this. So this is decreasing. Now from here, it will be increasing. But all the way from here to here is concave up. And that's the picture, right? I think you get the picture. I think you just have to look at the picture. I think it's quite clear where the function is concave up, where the function is increasing, then where the function is decreasing, and so on. As you can see, it decreases on the interval negative infinity, -1, right? Then it starts decreasing all the way from -1 to 3, and then from 3 to infinity will increase again. And then, as you can see, regarding the concavity, so it will be a concave concave down from negative infinity all the way to 1, and then from 1 to infinity will be concave up, right? Right? Anyway, so this is how you interpret this. I think I'm going to stop here with this lecture. There is one example in my notes. If you look at my notes, there is another example, and I prefer that you do it, or maybe I'll cover it at some point, maybe when we have a review session or whatever. So next time, the next lecture, I will continue with the curve sketching with asymptotes, and you will see what happens now. So now you have seen critical numbers, critical points, second critical numbers, inflection points. You have seen where the function on what interval is increasing, decreasing. Now you will see on what intervals the function is concave up, concave down. And now I would like to talk in the next lecture about something new that we will call asymptotes. And you will see that this will involve the limits at infinity, and we'll deal with that as well. So it will be a more of a longer lecture, but anyway, it will be fun. All right, guys, thank you very much. I'll stop here.